Thank you, everybody, for joining. I'm John Piddle, and I'll be covering TCP selective acknowledgement this afternoon in this afternoon session. And we're going to focus on learning about how this protocol feature behaves and how it impacts performance for TCP. So thank you for joining. Let's see if I can make this work. Yep. So what we're going to do is we're going to call out, we'll do a little bit of background information. We'll call out some relevant RFCs for reference. Then we're going to review some TCP acknowledgement basics as a foundation. And then I'll go ahead and get into an introduction of selective acknowledgement. We'll look at some decode details and quite a few examples. And then we'll see some Wireshark features that relate to columns, filters, and colorization that you can use specifically for selective acknowledgement to make it much easier to see selective acknowledgement in action. And then I have what I consider to be a pretty exciting example from a customer engagement where we can see selective acknowledgement in all of its glory, and then we'll do a wrap-up. So a little bit about me. I've been practicing performance engineering since the early 80s, doing protocol analysis since 91. I've been in professional services doing performance consulting since 2005. And I really get excited and love the mystery of a complicated performance issue. The session before lunch with the doctors are in. That was a whole lot of fun for me. And I shaved off my beard in 2003. So let's go ahead and get started. I'm going to go through the background information fairly quickly, but please at any point feel free to ask questions for the folks that are on the Zoom webinar. Hopefully they can all hear me okay, and feel free to ask questions also at any time. So just some related RFCs for you to be aware of, starting with the original TCP RFC in 1981, 793. That was pretty much the gold standard with regard to acknowledgement until 1996 with RFC 2018, where selective acknowledgement gets introduced, and then there was an extension to that in 2000 for duplicate SAC. These are good references for you to know about in case you've never read an RFC before. It's worthwhile just to take a peek to see what's there, to see what the language looks like, how things are described, because that's what we end up seeing through Wireshark as we're doing our decodes, is the behavior that's called out in the RFCs. So a quick review of standard TCP ACK behavior, and hopefully this won't be too much of a surprise to anybody, but we'll use this as a baseline. So as long as packets arrive in the expected order, you would expect to see the receiver will ACK not every packet, but every other packet. Now, if a packet arrives out of order, then we're going to see that the receiver will immediately issue an ACK with a value equal to the sequence number that was expected. So if we get something out of order, the receiver is going to signal back to the sender, hey, I just got something out of order. And the receiver will continue to ACK every packet until the expected packet is received. And that's the mechanism for helping to ensure that the TCP stream is received in the correct order. If a sender receives 4 ACKs with the same ACK number, which we call a triple duplicate ACK, hopefully that's a familiar term for folks in the room, triple duplicate ACK, then the sender will retransmit the missing segment. Now that's assuming that you have TCP fast retransmit and recovery is available and it's enabled. So these terms of fast recovery or fast retransmit and recovery, there's other sessions this week covering other aspects of TCP that explain those in more detail. So I want to introduce a really important term on the next slide. We don't tend to talk about this term, but I want to make sure that we give it a proper name. And that is the ACK that we refer to when we're looking at summary level decodes. We'll just say, oh, it's the ACK field, but it actually has a very specific name, which is cumulative ACK, and that goes back to the original RFC back in 793. Sometimes I know I was confused about this for a long time, but I've double checked this multiple times. So the value that you see in the ACK field represents the stream bytes received in order up to the point when the ACK was transmitted. And the receiver is in essence declaring, hey, I've received everything in order up to ACK -1. So I've got it all in order. It's been received in the proper order. And the next byte that I expect to receive is what's in the ACK field. So whatever I put in the ACK field, hopefully when the sender sends me the next bit of stream, that's what I'm going to see in the sequence number field. Now, selective acknowledgement was proposed in RFC 2018. It's an enhancement to the ACK mechanism. And the whole idea is we want to selectively acknowledge segments that have actually arrived out of order. So we want to give the receiver a mechanism to say, hey, I received something. It wasn't what I was expecting, but I want to let you know what it is that I received. And now the sender has a bit more information about what I may or may not have to retransmit. So the sender won't have to retransmit those segments if we know they've been received, but we can't accomplish that with just the cumulative ACK field alone. We need some additional signaling mechanism to make that work. So selective ACK is an addition to the TCP options field of the TCP header, and the receiver can declare up to 4 distinct segments or segment ranges using the TCP options field. So up to 4, unless the TCP timestamp option is also being used. If TCP timestamp option is being used, there's not enough room in the options field to do more than 3 continuous blocks of segment ranges for SAC. So SAC is on pretty much any modern operating system. TCP SAC is going to be enabled. If you're working with systems that are older, you might see that it's not enabled, but these days it's going to be on by default. It's negotiated at connection startup. And when we look at the SYN packet and the SYN ACK packet, you'll see SAC permitted, which means whoever sent that packet, whether it's the client who sent the SYN or the server who sent the SYN ACK, saying, I'm willing to do selective acknowledgement. I'll process that field if you send it to me. And each side can independently choose. So the whole idea is we want to inform the sender with better info about the success of segment delivery. We want to minimize the amount of unnecessary retransmissions. And this is a key point, this third bullet. It will not necessarily change congestion control algorithms. So just because you're selectively acknowledging and using the SAC field, it's quite possible and quite likely that packet received out of order, packet loss, will still result in closing the congestion window and throttling TCP. And we're going to see a lot of examples of that coming up in the field example. So any retransmissions may still have a negative effect on the congestion window and related timers. So just a quick show of hands. Has everyone heard of the congestion window? So I got 3 hands and a bunch of heads. So that's good. Okay. Very good. So when you're using Wireshark to do your packet analysis, you want to be able to feel comfortable using the SAC fields to help you understand the extent of which packets are arriving at a sequence. One of the key metrics that you want to focus on in addition to SAC is also bytes in flight, which Wireshark calculates for you automatically. You can make it's part of the TCP section, and you can also make it a column header. But bytes in flight, if that number stays low, chances are you've got a throttling issue and SAC is high, chances are you've got a throttling issue due to out of order or missing packets. If in-flight data or bytes in flight stays high, then that's an indication you don't really have a performance issue because the sender has not throttled back. The sender is still able to send the full congestion window and achieve high throughput rates. But if in-flight data dips or you frequently see slow start, you may find the root cause is significant out of sequence packets. And we're gonna look at some examples of exactly what we mean by segments that were received out of order, and some new terminology that's very much SAC specific. So the good news is Wireshark, as it can decode most everything, including log data, as we learned this morning, Wireshark can decode the SAC fields, and we're going to see some new values. SAC count is one new value, and left edge and right edge are new terms that are very specific to selective acknowledgement. So we're going to do an illustration now to take these concepts and put them into motion for you. So we're going to start with a pretty simple illustration. We've got a burst of 5 packets, 1 through 5. You can see the sequence numbers, length equals 10. But they don't arrive in order. There's one of them that arrives out of order. So you can see packet 4 shows up early, and packet 3 shows up quite late. So the order of arrival for this illustration is 1, 2, 4, 5, and 3. And we're going to use this illustration to really cement in the terms of SAC count, left edge, and right edge. So the first 2 packets arrive, and you can see, let's see if that works. Yeah. So there's that little square is the first packet, that little square is the second packet. Those 2 packets arrive, they're in order, everything is good. But here comes packet 4 now, which is out of order. And to understand the terms left edge and right edge, you can see the left edge arrow is pointing to that byte in the byte stream there, and right edge is pointing oriented to the right. So we're missing the piece in the middle. We're missing this white spot right here. But we did receive packet 4. So now we're able to at least inform the sender that, hey, I didn't get what I was supposed to get, but let me tell you what I did get. And then here comes packet 5, and notice that the left edge has not changed. It's still 41, but the right edge has pushed out to 61 because packet 5 arrived. It's part of, it's a natural sequence of following packet 4, and you can see packet 3 is still missing. And then finally, packet 3 arrives, and now all data received up through including byte 60 is ready for TCP. So any questions about this before we go on? Please. So the question was, does every other act change when you do selective acknowledgement? Great question. So that behavior doesn't change. And we've got an example coming up where we're going to look at the act behavior momentarily. But I wanted to leave that out from this first illustration just to focus on left edge and right edge. So we'll see that in just a moment. Any other questions? Okay, so we're going to look at some quick decodes. So here's our cumulative ACK, just just right where we're used to seeing it. All bytes have been received up through 1477, and I'm ready for 1471, but there's actually more information to share with the sender. And that information is down here. I've got a SAC block in the TCP options field. And so I've received something out of order. It's defined in the SAC block. So what is missing? Well, what's missing is, and if you did the math between what's in the left edge and the cumulative ACK, we would see that we're missing 14,771 through 17,618. So now the sender is aware of what's actually missing and what may or may not need to be retransmitted. So things that I've already sent, ideally, we won't see those retransmitted. Doesn't mean that won't happen, but for the most part, the sender will not have to retransmit what's in the selective block here, or the selective acknowledgement. Okay, also notice the packet length of the ACK field. Without selective acknowledgement in this example, it's 66 bytes. With selective acknowledgement of one block, SAC count 1, it's 78. And then with a SAC count of 2, notice it's 86. So sometimes you can just look at the size of the ACK packet to get a sense for how much is in the SAC block, how many blocks have been declared by the receiver. Okay, so let's look at one of my favorite features, which is being able to take any field that's in the decode, right mouse click on it, and apply it as a column. So here we were focused on left edge, did a right mouse click on it, apply as column, and now you've got a new column in your decode summary with that value. Like so easy, so quick. I'm a huge fan of using fields as columns and also colorizing rows based on the values in those columns. Okay, so to your question that you had earlier about, okay, how does this affect the every other ACK? We're going to look at the same example we had, but we're going to pay attention now to how the receiver responds back to the sender. So packet 1 arrives and receives, the receiver starts a delayed ACK timer. So who can tell me what is the delayed ACK timer for? What's the purpose of that? Say it again, please. Well, so if we're going to ACK every other packet, we can't wait forever, right? So first packet comes in, there's a mechanism called the delayed ACK timer. When that timer expires, we kind of assume that there is no second packet, so we'll ACK what we've just received. So the delayed ACK timer starts to count down. We start waiting for a second packet. So in this case, packets 1 and 2 have come in, which was sequence number 21 for a length of 10. So we ACK saying, I'm ready for packet 31, please. Packet 4 arrives, but it's out of order. So we immediately issue an ACK because it's out of order. So that behavior does not change. We ACK every other packet until we get something out of order. Packet 4 in this case is out of order. So we immediately issue the ACK and we include a SAC field block, one block saying, I've received 41 through 50, and the rightmost edge is 51. We'd be ready for 51 when that time comes. Here comes packet 5. It's also out of order. So we immediately ACK back to the sender, and we say, hey, I'm still waiting for 31. Oh, by the way, I did receive something, and now in my receive buffer, I've got 41 through 61 of the stream bytes. And at this point, and I'd really like to make sure you guys are comfortable with this, that the receiver stack is holding these two packets, and I can't hand those off to the application layer. Even if there's a push bit and an urgent bit, I can't hand those off to the application layer. And my question is, why can't we? Say it again. Because I don't have packet 3 yet, and packet 3 is important because we have to deliver in order. So you're right, we don't have packet 3. So I can't feed the data up to the application layer until everything is in order, because TCP promises I will always deliver data in order. Hopefully that's a familiar concept. Packet 3 arrives, and now the receiver issues an ACK for 61, saying I've received everything up through byte 60, and I'm now ready for 61. And we're going to see quite a few more examples of this to really nail down these examples. So packet 3 arrives, order is restored to the force. Yay, we like that. We like everything to be nice and tidy. Now we're going to look at something that's a little bit more complicated. We're going to look at 6 packets. They were transmitted in order, but due to a network problem, a really bad network problem, they're arriving in kind of a helter-skelter order. And you might think, boy, this can't really happen. Like, could it really be this bad? Sometimes it can, sometimes it's not this bad. When we get to the real life example, we'll see how bad can be. So this is our next example. It's more complicated. As we go through this, it might feel a little bit like we're being shot out of a cannon. I promise it won't be that bad. We will get through this. So the order is 136452. 136452. So packet 1 comes in. We start a delayed ACK timer. Packet 3 arrives next. So we use our ACK, our cumulative ACK, and our SAC field to indicate what we've received so far in order and what's currently out of order. Here comes packet 6. Notice now that we have 2 SAC blocks defined, 31 through 41 and 61 through 71. And you can kind of see from the example what's missing and what's been received, at least visually. Packet 4 arrives, and notice that the right edge of the first block is incremented from 41 to 51 because we've now received that portion of the stream bytes. So now we still have 2 SAC blocks, we still have 2 missing packets. And when the receiver gets this information, he'll have a perfect idea of what's been received and what's still missing. Here comes packet 5. And notice that we're down now to 1 SAC block, declaring, hey, I've got everything from 31 through 70. I'm ready for 71, but I'm still missing 21 through 30. So pop quiz, how many packets are in the sender's retransmit queue? Think about you as the sender. I have to be aware of what's been sent but not yet received or acknowledged. And I have to keep those in a retransmit queue until the sender says, I've received them. So take a crack at how many packets are in the sender's retransmit queue. And we can start with this one here. Has this one been acknowledged? Whoops, that one. So I see some tentative, I think so. Yes, it has been acknowledged, right? Because we can see cumulative ACK is 21. So 11 through 20 has been acknowledged. That's not in the retransmit queue anymore. However, there we go. 1, 2, 3, 4, 5. 5 packets are in the retransmit queue on the sender because they have not been fully acknowledged by the receiver as been received in order. So the answer is 5 on the sender. You guys good with that answer? Okay. How many packets are in the receiver's queue? 4. Who said 4? Yep. So I like that answer. I agree with that because they're there and I can't hand them off yet to the application layer because I'm still waiting for packet 3. Packet 2 I'm waiting for. So packet 2 finally arrives and now our SACs go away and our cumulative acknowledgement is now 71 saying I'm ready for sequence byte 71. Any questions, concerns about that? Because there's a concept of if the receiver runs out of memory and I have to sacrifice something, I might have to sacrifice something that's waiting to be given to the application layer. So the cumulative ACK is the gold standard. The selective ACK helps me avoid any retransmissions.
So the sender is going to assume there's not enough buffer potentially on the receiver side
until it's been received in order. That's right. So once we get to this last state here, now there's nothing in the retransmit queue because it's all been acknowledged in order. Yeah. Okay. Any questions from my Zoom participants? Nope. Okay, great. All right, we made it. We did it. We got through the second example. It could have been a little bit hairy at first. Some of these concepts, at least for me, when I started to think through this whole SAC stuff, and you'll see the example in a minute that had me busy for over a month. It just, I would think I would get it, and then I would see something and then realize maybe I didn't really understand it. I had to challenge myself to just double check my understanding. So we made it through our example. I'm excited about that. So some more decodes. So here's an example with 2 SAC blocks in our decodes. And you can see hopefully down here, SAC count is 2. And then you can see left edge, right edge for the first block, left edge, right edge for the second block. And then up in I made a column, SAC count, and then we've got SAC left edge, SAC right edge. I'm going to explain this phenomenon in just a second because that looks a little bit weird, right? Where you've got 2 values for left edge and you've got 2 values for right edge. And I'll explain that momentarily, okay? So here's our zoom in. We've got the two blocks in the decodes. And notice that I applied a different profile, which I'll explain in just a second. And now we've got SAC left edge 1, SAC right edge 1, SAC left edge 2, and SAC right edge 2. So now I've got a separate 2 columns for each block, left edge and right edge. And I have Saki to thank for that because I showed Saki that first picture and I go, dude, I can't work with that. That doesn't help me. And he goes, oh, you just need to do edit occurrence. If you notice that says occurrence right here. So there's certain decode fields within Wireshark where there's multiple occurrences of a particular value. In this case, there's 2 SAC blocks, or there could be up to 4 SAC blocks. So you could have 4 right edges and 4 left edges for a total of 8 possible columns. So when you edit a column, so you right mouse click on a column header, select edit column. Anybody done that before? Yes. I mean, it's fairly common to change the name of a column. And you'll probably notice that occurrence is always part of that. You might have wondered, I wonder what that's for. And it's usually occurrence 0 is the default. Now you know. So let's also talk about coloring and filtering. So notice I set up a color rule. Actually, I set up 3 color rules. each with a different filter. So we've got TCP options.sac.count equals 1 for yellow, equals 2 for dark yellow, and equals 3 for red. I'm sorry, red for equals 3. So now when you're looking at the decode summary, you can get a quick idea of where do I have the most SAC blocks, because wherever you have this most SAC blocks, you have the most what? If I have 4 SAC blocks, what is that telling me that's important based on what we saw earlier? We've got a bunch of out of order packets, and not only out of order packets, but portions are together and portions are out of order. So they're coming in this kind of random order. Yeah, so coloring is really valuable. In the packet doctors, you saw the doctors use coloring rules to identify SYN packets. I think it was Saki who used a rule to say, hey, if the delta time was greater than 2 milliseconds, I didn't know you could do that. So that was a really valuable session for me this morning, that you could use really complicated filtering values for your coloring rules. Anybody use coloring rules before? Good. Yep. Yeah, they're like so valuable. Okay, that's that. What about duplicate SAC? So you're going to hear the term duplicate SAC. That was defined in this RFC 2883. Most important thing to know is a duplicate ACK is nothing to do with a duplicate SAC. It's the terminology is a little unfortunate. So duplicate SAC basically means the receiver can inform the sender, even if something is not out of order. I could be saying, hey, I just received something that I already have received. I've already acknowledged it, just want to let you know. So not at all like duplicate ACK. So duplicate SAC is just, it's a communications mechanism. Hey, by the way, sender, I don't know why, but I've already received this segment that you've already sent it to me, and you sent it to me twice. Those can be useful if there's some weird network conditions where you've got multiple paths and you've got a lot of retransmissions, and things that you've already sent have arrived around a path with a higher latency and just are arriving super late, which would kind of bizarre, but it can happen. And duplicate SAC can help you detect those. And Christian did a session in Europe last year for 2021, which is, he spent like an hour talking about duplicate SAC. It's a really valuable session, so I recommend that one. All right, we're gonna leave the theory and we're gonna leave the background and jump into an actual engagement where SAC was really important in trying to figure out a performance problem that a customer was having. So the amount of out of sequence packets wasn't just high, it was like off the charts, crazy high. And there's an illustration to help you see, what does that even look like? How would I know it if I saw it? And what was the impact on performance? So the scenario and background, there was a performance testing lab set up by the customer. They were getting ready to move things to the cloud. And they had set up this lab for automatically provisioning new VMs. So they wanted to automate spinning up new VMs and then building those VMs on the fly. So if you can imagine, there's an image server, somewhat analogous somewhat to like a boot P, vaguely, server. But the idea was, I'm spinning up, I reach out to my image server and say, hey, I'm a type 1 VM, give me my image and help me build myself. So a lot of data being transferred across the network to build this VM. And the performance in the lab was so bad that they had to put a hold on their migration. They're like, we're not ready. We can't build, it takes 10 minutes to build a server. That's not acceptable. We got to figure this out. So they worked for a while on it, and then they gave us a call. I was assigned to go visit with them. It was a really interesting engagement. Here's the lab configuration. So this is the image server over here where all the images were kept. Here's the new VM to be provisioned down here in what they called this public security zone. There's an IPS device, a firewall, some routing between these different zones, another firewall, another IPS, and you can see where we had captures. So we had 2 capture points, one closest to the image server and one closest to the new VM that was to be provisioned. And there's a 1 gig link with no other traffic in the middle. And it was still slow. It wasn't just slow, it was like really, really slow. So that was our lab configuration. And if you can imagine, you've got IPS vendors, firewall vendors, switch vendors, router vendors, they're all going, it's not me. It's got to be them. My stuff is good. Everybody had a green indicator. Everybody's good. So everybody's innocent. My job was to help the customer figure out why throughput was so low and help them get to identify the right vendor who was causing the issue. So we're going to take a quick look at the nature of this problem using some advanced analytics. So we have some tools where Wireshark is at the core, and we have some analytic wrappers around it. And I'll just quickly show you what some of the analytics were saying. So we have this transaction, the set of traffic, not a lot of time, 3.5 seconds, but half of the delay, more than half of the delay, was actually TCP related delay. It wasn't the server, it wasn't the client, it wasn't the network, it was the protocol. And that's what that purple wedge tells us. We can see that we whoops, come back. We moved 48 megs of traffic. There was 117 retransmissions in the lab. There's nothing on this network. It's a lab network. 49 out of sequence, 20 triple duplicate, help me out here. Triple duplicate acts. Thank you. Okay. Before we look at the next metric, what does bytes in flight tell us? It's a pop quiz, another pop quiz. Bytes in flight as measured by Wireshark. Say it again, please. It can, but how do we observe that? Yes, but it's the number of bytes, packets inferred, but yeah, the number of bytes that are on the network that have not yet been acknowledged. When that number is high, the congestion window is wide open, which is a good thing. When that number is low, that's a bad thing. Throughput is stalled. We can't put a lot on the network until it gets acknowledged. So good. So the number of stream bytes outstanding, we just said that. So it usually reflects the sender's congestion window, to your point. And that's Frank back there? Hi, Frank. Okay. So that analytic tool takes our Wireshark capture and then draws us some charts. And this chart at the top here is in-flight bytes. And you can see it goes up, it comes down, it goes up, it comes down. What does that behavior look like? Slow start. Right, so the congestion window is opening and then it's slammed shut. Excuse me, and then it slowly opens and slams shut. So if we look at it a little bit closer, you can see, hey, I got up to like 50K, slam shut. There's also some indications of retransmissions, triple duplicate acts, and so forth. So remember I said if in-flight byte stays high, there's really not a lot to look at. But if in-flight byte stays low or has this behavior, then we've got a performance issue we've got to figure out using Wireshark. Oh, sorry, this last one, notice it never peaked again. It pretty much stayed flat. Okay, before we get into this example, any questions about or clarification around in-flight bytes? I can tell you after the session, yeah. I got a cough real quick. Hang on one second. Even though I'm drinking water. Okay, I'm back. I hope for the folks on Zoom that didn't come through. All right. So now what we're going to do is we're going to look really, we're going to get out a microscope. We're going to get out an electron microscope, and we're going to look at a series of packets and their arrival to just see how bad is bad. So we're going to use time-lapse photography. We're going to step through 19 packet burst. And this is going to show us the number and nature of the sequence packets because it was just off the charts crazy. And I had to get to this level of detail for me to challenge router, firewall, switch, IPS, the vendor, to say, this is what I'm seeing, and then I'd have to explain it. So I had to feel like I was on top of my game. So we're going to see how out of sequence can impact performance and how we can use the SAC field to determine just how bad is it. How bad is bad? That's what we're going to do. So we're going to focus on these 19 acts, and again, in great detail. Each act corresponds to one or more of the payload packets in our sample. And again, I just took a random sample. It was such a mess. It didn't matter really which random sample I took. I just took one at random. And then we're going to use these acts to look at the arrival order for these 19 packets. So before we get started, because I like pop quizzes, as you guys can tell, why are there so many acts? I thought the receiver is supposed to act every other packet. Anybody in there? Okay, you guys out there on the webinar, you're supposed to do these pop quizzes too. So remember how we started. We said, what's the normal behavior of TCP? What do? We act every other, unless what? Unless they're out of order. So the answer is, why are there so many acts? Because everything's out of order. Why does the act packet size change? Remember, there's no payload, right? Length equals 0. These are all act packets. Why does the packet size change between 66, 78, 86, and 94? The number of SAC blocks, that's right. The bigger the number, the more SAC blocks are in there. Why does the client's receive window continue to shrink? See, it starts out at 44,416, and down here it's at 17,280. Why does that number keep going down? Because it has to keep packets in its receive buffer. I can't hand them off because they're out of order, right? I have to wait. So this is what, when I was asking earlier, how many packets are in the receive buffer, this is one of the ways you see that is through the Windows equal size. When it's going down, for various reasons, TCP cannot hand off to the application layer. One of the reasons is they're not in order. Another reason is the application is so busy he can't take the packets. I've seen that as well. That's not the case here. And then why do we see so many duplicate acts? We sort of already said the answer, because there's out of sequence packets, right? Questions before we get started? So we're going to have to fasten our seatbelts here to get on our way. Anybody ever ride Mr. Toad's Wild Ride at Disney? Nobody? I've had people in Europe say yes to this, by the way, because they have Mr. Toad's Wild Ride I think in Disneyland Paris, I think. Anyway, Mr. Toad had a wild ride at Disney, and we're going to see what that looks like here. Okay, pre-departure, we've got 19 slides. They're going to go quick. It's kind of like watching a film strip. The top portion is going to show you which packets in the burst have been received. The bottom portion is going to show you ACK and SAC. And then each slide represents a new packet being received, and the state, and this is kind of a key word here, the state underlined of all previously received packets. So some quick orientation. Here's our list of 19 acts. The far left column is the system being built. So that's the client who says, hey, I'm a new VM. Where's my image? Help me get built. I want to be a real VM one day. I want to grow up to be a real VM. The second column is the frame order as seen on the server side. So we basically have got two captures that I've put together in an Excel spreadsheet just for this purpose to help explain this. So we've got far left is closest to receiver. The second column is closest to the server. We're going to use a red line to indicate the packet that was just received. So that's our state information. This is what was received. And we're going to use green lines to show what was previously received. And then down in the bottom, this will be a little hard to see from the back. I've got the header showing cumulative ACK. And then I've got the TCP options field, which is the next build out, the value of the SAC from the TCP options field. So that's it. That's our orientation. We're going to look at 19. It'll take about 3 or 4 minutes, but I promise you it'll be pretty dramatic. So fasten your seatbelt, focus on the cumulative ACK and the SAC values as each packet is processed, because that'll really help you challenge your understanding. Did I really get these concepts? So at the beginning of this sequence, the sequence number was this big number. Just focus on the last 4 digits. I didn't have relative sequence numbers turned on. I wish I had. I just had the absolute numbers turned on. So, all right, everybody ready? Okay. All right, here's the first packet that was received. So they were transmitted from top to bottom. They were received. What we're looking at is we're seeing the receive order. So first packet was received, and after that was received, notice that we have cumulative ACK saying, hey, I'm still waiting. I just received something. I'm still waiting for 6095. And oh, by the way, I received this block of stream bytes from left edge to right edge. So I've got one SAC block and cumulative SAC saying, hey, I'm still waiting for that thing I've been waiting for. Second packet, somehow we jump like 4 or 5 different packets in the stream. And now notice I'm still waiting for 6095. And now I've got 2 SAC blocks in my TCP options section. Third packet received. Now I got what was supposed to be the first packet that showed up as packet 3. Notice that the cumulative ACK has been updated now. Why? Because I got the thing I was waiting for. And the SAC field has not changed. So take a guess as to why the SAC field has not changed. Exactly. So what we just received is what we were waiting for from the beginning, right? These are still this is the state of what's been received, what's in green. So you're right. I like the way you said it. I like the way you said it better. So here comes packet 4. So packet 4 is a huge jump down, right? And notice that the right edge of this block has changed to reflect this red box. So the right edge has moved out. It didn't make any changes to the second block because the second block hasn't changed. Okay, so far so good. Ready for packet 5? Okay, here comes packet 5. Now packet 5, whoa, come back. Packet 5 adds to this block right here. So you're going to see that we've extended out the right edge of that SAC block to say that, so previously we just had this green box. We've added to it, what's the term? Contiguously? It's contiguous, right? So now the right edge changes to reflect the fact that this is part of what's been received. And something else happened that's not so noticeable. It's not horribly important. It's just worth noting. These two blocks flipped, which means the RFC says you can maintain order or not maintain order. You don't have to, right? So if we go back, can you guys kind of see down here? I would say it's in terms of the block order, it's up to the implementer. Yeah. Okay. Okay. So SAC blocks have changed. Here comes packet 6. Notice it's filling in a gap, right? So now the cumulative ACK, and I did some extra columns just to make it the math easy. The extra, the cumulative ACK should now be 887. And notice it's 887, hard to see from back in the back. ACK is 887. And we got rid of one of our blocks. Why did we get rid of one of our blocks? Because you don't need it anymore. It's been, the cumulative ACK now reflects the fact that it's all together. Because basically, these 3 packets became whole when that one was received. If I can say that terminology. Okay, here comes packet 7, way down, it's like, whoa, way down there. Now we're back to two SAC blocks. Here's packet 8. How many SAC blocks do we have now? 3. Now we got 3 SAC blocks. Here's packet 9, which fills in that top group. So now we have an updated cumulative ACK. Packet 10, packet 11, packet 12 and 13, guess what? They actually came in together. They're the only 2 that came in order of this whole exercise, 12 and 13, packet 14, 15, jumping down to 16. Now this is interesting because now the left edge actually got updated. Let me go back one slide. So the left edge here is pointing to this packet, 15. When 16 comes in, we're actually moving that left edge higher up the stream bytes. So now the left edge has been updated to reflect the receipt of this packet. Packet 17, whoa, 18, there's only one left, packet 19, and now it's all together. No more SAC fields. The cumulative ACK should reflect 5055. That might be a typo. I was going to say it should reflect that because that's what we've received. And that's it. We did it. All 19 packets have been received. Huge cluster. You know, I think I could say to the switch vendor, you know, I don't think this is you, switch vendor. This is not a switching issue. This is something else. So we did it. It was a long, strange journey, but all the data has been received. Questions, comments about this? Yes. Dude. Yes. Yeah, it was the IPS. Okay.
Does this tell you what the cause was?
You have to kind of infer the cause, because this behavior of bouncing around just huge gaps suggests that data is getting queued someplace It's being like a store and forward type of model where packets are being queued and stored for some purpose, like an IPS, because that's what IPSs do. They have to inspect the signature of the payload, and you often need to have more than one packet in order to inspect the payload. Now, the fact that this was all SSL traffic, it's like, what are you inspecting? You can't inspect SSL. So, but yeah, so the answer is not directly, but when you can show the behavior or at least explain the behavior, you can rule out certain things and rule in other things and have a different kind of discussion with the vendors. Well, hey, turn those IPSs off. Not only turn them off, unplug them. Because turning off, it's like, is it really, really off? I mean, I want it powered off. I don't want a cable running in it. I just take it out of the picture completely. So definitely some sort of buffer management issue, first in, first out, last in, first out. I don't know. It was some UFO effect. I have no idea. So let's see. We have to do a time check because I'm not, do I have like another 15 minutes?
Yes, you're to 2:15 or 3:15.
Okay, so I wasn't sure how long it would take to go through this. So this was actually a possible endpoint, but there is an appendix of some other stuff that we can talk, like what was the outcome from the lab study? Because that was a question, right? So the client was happy. We could help them understand the full extent of the problem. Like it's not enough just to see, oh, there's out of sequence packets. What word would make sense? Not velocity. What's the range? I'm not sure if that makes sense. There's a word I can't think of it right now. The extent of how bad it is. I mean, the fact that you saw it jump like 8 packets and then jump back up and then jump back down, that behavior of jumping around was kind of instrumental in saying IPS. And it definitely created a performance impact because the sender's TCP stack is getting all these indicators of packet loss. So the congestion window was closing, it would never open back up again. And that's why throughput was so low in the lab on a 1 gig link with no other traffic. So I was with the client it's not that you go to battle, but you have to defend, right? When you go to a vendor and say, I think you got a problem, you have to defend that. So we had data to defend it. We could show with some clarity. And the vendor said, well, we think you're probably right. Let us go back and look at our algorithms. And a few months later, they tested a new model in the client's lab. And there were some improvements, but they still had some issues. But the good news is there was a dialogue that started. They said, it looks like us, we're going to address it. And, mission accomplished. So some reminders, you can quickly determine presence of SAC using a display filter, coloring rules. These are really great tools. When I post this deck up to the retrospective page, there'll be a small capture. Unfortunately, I can't find this capture. I don't know what happened to it. If I do find it, eventually I'll post it, but I have a smaller capture and I have some profiles that you can use that do color filters and also the columns. So you can look at that and explore them. Those will be posted after the event on the retrospective page. Remember tcp.options.sac.count. And again, creating custom columns. It's so easy. You kind of you don't realize how powerful it is, but it's so powerful. So focus on bytes in flight. If you see the congestion window constantly closing, you have an issue. If it stays big, nothing to see here. It's all good. That exercise, that 19 slides, probably took me 2 to 3 weeks to just get my head around it. It's like, I don't understand what I'm seeing here. This makes no sense. But I couldn't stop. My wife tried to get me to stop. It's like, I can't, I got to figure this out. Okay, it's prudent to interpret some of them and make a high level assessment. I'd probably say don't get lost like I did in the SAC mines. but it was a good experience for me for sure. If you have a lot of sacks with 3 or 4 gaps, that's probably not a good thing. If you only have a few, I mean, it's the age of the internet. Almost all of our traffic today goes across the internet. If you have SD-WAN, if you don't have MPLS anymore, you know, work from home, everything's on the internet. There's going to be data loss. There's going to be out of sequence. It's just unavoidable. The key is how bad is it? And you can use SAC count to help with that. It's definitely a throughput killer. We saw that. The extent to which it's a throughput killer kind of depends on the operating system and the patch level, and even the NIC driver to some extent. If you guys have worked with NIC cards that have something called TCP segmentation offload, is that familiar? Right? So if you see that, or if you see that as an option in your NIC properties, what you're basically saying is you're saying, okay, NIC card, I really know nothing about you, but I want you to handle TCP stack operations. I want you to handle certain things. I want to offload from the CPU and the operating system. So be aware of that. The SAC field on the sender, retransmit queues could grow on the you know, because again, we have to maintain all the packets in the retransmit queue, impact on the receiver, memory. I think we saw the impact of all of this. So a few reminders: use columns, use profiles, use colors. There's one other thing that could happen depending on what firewalls you have in the environment. There's some firewalls that'll do something called sequence number randomization. Is that familiar? You guys heard of that? It kind of goes back a few years. Some firewalls it's on by default. Some firewalls you have to turn it on. In the early days of SAC, the firewalls didn't know what SAC was. So they would change sequence numbers, but not update the SAC field. And then you got who knows what kind of mess that created. And I think I have an example of it here. Notice this will be hard to see a little bit. See this ACK number ending in 7932, 147, 7932. Down here, it's nothing, it's not even in the ballpark. It's completely different numbers because the receiver created this field. It went through the firewall back to the sender. The sequence numbers got randomized up here at this layer, at the summary layer. Sorry, what was the name of this ACK again? Cumulative ACK. So the cumulative ACK got randomized, but it didn't do anything to the SAC field down here to update it, the firewall at that time. I don't think this happens a lot anymore, but if you have firewalls and they do have sequence number randomization, just be on the lookout. Okay, and there's the example of what I just showed you. I'm sorry? Or it just gets ignored. You know, if I'm the sender and some receiver sent me something that looked like that, I'd pretty much just have to say, I don't know what this is, and ignore it. At least ignore the SAC part, because it doesn't relate to anything that matches what I'm doing. So, who remembers The Godfather? Hey. And Tony. Yeah, so SAC is not a promise. This is the question that you had earlier about why can't I just acknowledge it? Because SAC is not a promise, and there is something called in the RFC, there's something called renege. I can say I received it, and then I can say I don't have it anymore. I had to sacrifice it. So the receiver is permitted to discard data in its queue, and that's called reneging. And I think we're just, these slides are in there. There's some additional details, and that's it. So I hope you found this interesting and exciting and a little bit of a wild ride. So any questions, comments? Anybody out in Zoom land on the webinar? So we had an example of that in the doctor's. No, there were these gigantic frame sizes, 16K, 17K, 20K showing up, because where Wireshark and WinPCAP grabs the data for the decodes, it's before it gets to the NIC card. So if you can imagine, it's kind of going from the stack down to the NIC card, and you see this gigantic packet showing up in Wireshark, because that's where we capture is from memory, right? It gets to the NIC card, and then the NIC card carves it up into segments. That's the segmentation offload concept. And think about it also from an ESX standpoint or VMware. It may have its own segmentation offload on the physical NIC of the ESX server, which is working on behalf of hundreds of VMs, right? So, but where you're seeing it, like in the case of VM, it's within that operating system, you're picking it up on its way to the virtual NIC before it actually gets. And I've seen packet loss inside of ESX hosts. It took a long time to find it, but like looking at traffic coming in from the switch to the ESX host, traffic is there, doesn't show up at the VM. ESX was dropping it because it was over provisioned and undersized. Any other questions, thoughts, comments? Well, thank you guys for coming along this wild ride with me. I hope it was fun and interesting.